So, hi everyone. Welcome to the live section of this course, which is Quantum Transport. I'm Gitanjali. I'm a PhD scholar from IIT Delhi, and I'm the TA for this course. So, in last week, we have covered up to, I think we covered all the parts for week 9, and we have also covered few parts from week 10. So, for this session, we'll go through in detail about the concept that has been covered. Okay. Let me see. Okay. So is it audible now? Let's see. Okay, so is it audible now, my voice? Is it okay from your side? So in the last session, we covered up to the concept up to week 9, and we have tried to solve few problems related to the concept of week 9. So for today, we'll go through in detail about what has been covered in week 10, which is basically what are the different type of chart sensor, why do we need a chart sensor, and also we will covered what are the devices that we can use for sensing ultrafast charge detection, which is in the order of maybe microsecond or nanosecond range. So let's start. So in the first part of this week, so we have seen why we need a charge sensor. Why don't we use the conventional detection technique? So the reason is that so it is quite obvious from the Coulomb blockade reason. So if you recall, when we change the gate voltage from let's say we are going from the right side to the left side, then the week 10 assignment also is both from week 10 and week 11 concept. I don't think so, but I have seen all the question. I think it's all from week 10, not from week 11. Okay, so that's why I won't cover week 11 for today. So for okay, let's start. So why do we need a charge sensor? Why don't we use the current one? So this is because of the limitation of experimental setup. So whatever when we measure the current, so we measure the current through the tunneling rate. So if the tunneling rate is really low, then in that case, then it's not possible for the device to measure the current. And so for that case, if the current is already low, then it can't detect the charges. Even if there are charges that is tunneling through this quantum dot, then we may assume that the current, because the current is zero, then the quantum dots are all tunneled out. There is no electron that is tunneling through this quantum dot. But in reality, this is not the case. And this is because of the limitation of the experimental setup or the device. So this is quite clear from this. We have seen this stability diagram. So when we go from the right to left, then we are increasing. Sorry, we are decreasing the gate voltage, and we can see that. So decreasing the gate voltage means, if you look at this figure, we are changing the tunnel barrier resistance. So from the right side, if we look at this figure, The tunnel, the source and drain tunnel resistance, they are quite thinner. So that means that in the right side, the tunnel rate is quite high. But when you go to the left side, that is by applying a higher gate voltage, then in that case, what happens? The because of this gate voltage, the barrier, which is close to the source and drain, they become thicker. So because of this thicker barrier, then the tunnel rate will now decrease. So because of this, what will happen? The when we go from so when we increase the gate voltage, then the current will gradually decrease and will reach a point where the current is not measurable by the device. So in that case, instead of measuring the current through this quantum dot to detect the charge, the charging and discharging event, in that case, what we can do, we can use sensors. The sensors can be a quantum point contact based sensor or a single electron transistor sensor. So they are like the indirect method. So it's like we are not directly measuring the current through this quantum dot. So we are making some a reason around this quantum dot. The reason can be the quantum point contact for QPC based sensor, or it can be a single electron transistor which is close to this quantum dot region. And this QPC and the SCT which is close to this quantum dot region, so there will be a quantum dot region where we are seeing the charging and discharging event, that is the tunneling event. So we are seeing this quantum dot, but we are measuring the this charging and discharging event through this QPC or this SCT based sensor. Recall QPC, it's like a construction, 1D construction we have seen in details in our previous live session. And SCT is like another Coulomb block weight device. Like there is a quantum dot, there is a last quantum dot which is connected to both source and drain, also to a gate. Okay, so these are different types of quantum dot, and but the sensitivity of these sensors, they are typically low. And so to increase the sensitivity, we'll see a radio frequency SCT based sensor. So the reason behind, so as I said, the reason behind this QPC, why we are using this QPC or SCT based sensor, because of this low current, low tunnel current through this device. So let us see. So if you look at this slide, so they basically tell us about what are the different reasons where the device can operate to show you a charging and discharging event. So if you look at this graph, so this is the current versus the electron transmission rate. So if you look at around the frequency 10 to the power 5, 10 to the power 5 hertz. So beyond this 10 to the 5 hertz, that is in this region, so you can see that so for this device, the noise floor, it is around 10, it's in between 10 to the power minus 13 to 10 to the power minus 14. So that means if you want to detect a charging and discharging event, so this current, the current should be above this noise level so that you can detect the current. So this is possible in the high frequency region from beyond 10 to the 6 to 10 to the 9. So megahertz to terahertz, 10 megahertz. Beyond megahertz region, you can detect, you can use the current sensor to detect the charging and discharging event. But below this 10 to the 5 or below the megahertz region, below the region where the tunnel rate is in the order of megahertz or in the order of kilohertz or some hertz. So beyond below that, what will happen? You can see that in this figure, the noise figure is here, and the current you are measuring, it is below the noise level. So that means whatever current you will measure, it won't be detected by this detector because of the high noise level. So the signal to noise ratio will be much lower in this low frequency region. So this is why we need a charge sensor, which can be the QPC or the SCT based charge sensor. So let us see in brief the what are the classical charge sensor that we use for charge detection. So so classical charge sensor, it's like a field effect transistor. So whenever the charge configuration around this device changes, then the field changes, and according to that, we can detect the electron tunneling. And this classical charge sensor, they are not they cannot be used because for sensing in the order of millisecond we can't use this classical charge sensor, or in microsecond or nanosecond we can't use it. It's because that these devices they have larger geometry and they have larger capacitance, which make them much lower. And because they are classical devices, you can see low signal to noise ratio. That is, the noise will be much higher in this classical FET based sensor. And you can see that you can detect only one electron in 100 millisecond. So that is why we can't use this classical FET based charge sensor to detect the charges in which we want to detect in the order of microsecond to nanosecond or much lower than that. So let us see what are the two types of QPC and SCT based charge sensor in brief. So recall for QPC based charge sensor, we have seen a variation of conductance as a function of gate voltage. So when we vary the gate voltage, we see that the conductance changes linearly. Then we see a plateau region. Then it again changes. Then plateau region. Then it changes in this manner. So if we use these characteristics, and if we design a QPC around this quantum dot region, then depending on the charging and discharging event, then the conductance of this quantum point contact, they will change. So according to that, we can see the charge sensing. So for that, if you look at this plot, the single electron detection, this figure. Okay, so there is a quantum dot which is one electron. Let's say this is in one electron region, and we are increasing the gate voltage in the negative direction. So what we are doing, we are increasing this gate voltage Vm, and we are measuring the conductance through this quantum point contact. What happens when this we are increasing this gate voltage, and what happens in this quantum point contact region? So if you look at this figure, we can see that when we increase the gate voltage, then we will obviously see the same characteristics. So the current will increase, so there will be a bump here, then the current will increase. So keep in mind that these are the conductance through this quantum point contact region, no, not from this quantum dot region. Okay, so we are indirectly measuring the response here. So this is the conductance graph for quantum point contact, which has same characteristics like this one, which we have seen before. And this purple graph, this is like the what is the change in conductance as a function of gate voltage. So this is like a dGQPC over dVm. Okay, so because of this charge tunneling through this quantum dot, when we increase the gate voltage, what will happen? The conductance of this QPC region will change, and it will have a bump, then it will increase linearly. Okay. So if you look at this figure around towards, if you look at the right side, for the right side, the quantum dot, it is inside this, the electron is inside this quantum dot region. But when you go to the left side, the electron, it is tunnel out to the quantum dot. So that means around this bump region, what is happening? The electron is tunneling from this quantum dot region to the drain side or to the source side, depending on the gate voltage. So it is like the electron is tunneling out, and because of the electron is tunneling, the conductance of this QPC is seeing a bump here. So that means if you for this curve, for this orange, uh, okay, let me take this one. So for this orange curve, if you calculate what are the variation of the conductance, so around this bump region, you can see the conductance is changing rapidly. So that means if you plot the derivative of it, that means it will have a sharp peak around this transition point. And if we measure this transition point, and if you use it as a sensor, if we use this reason, then we can tell the charging and discharging event, and we can sense the charge through this quantum dot reason. So this is the basic principle of quantum point contact to measure the charging and discharging event. Okay. So, so these are some of the examples that has been covered in the lecture. So let me just tell you in brief what this graph says. So this is the charging and discharging event when you have a single quantum dot. So you have a single quantum dot and you deposit the quantum. So this is the quantum dot region, and you have a QPC channel here to measure the change in conductance. So if you look at this figure, this is the conductance through this QPC, and these are the Coulomb blockade oscillations. Okay. So that means one thing you can notice here is that, or let us say, whenever there is a change in conductance in this graph, there is a peak here. So that means we can use this region as a chart sensor. Also, if you look at this, so the more conclusion you can get it from this figure. So it's like when we, for this experiment, when they have decreased the conductance or they increase the conductance in the negative direction, you can see that the this first plot, it is for the current through this quantum dot. Okay. And for the second plot, it is like the conductance through this QPC region. So when we increase the gate voltage in the negative direction, you can see that the Coulomb blockade oscillation, the peak, it is gradually, it is not detectable here, but it is detectable here, but it is highly detectable here. So that means if you look at this region where the current is much, much lower, then we can't use this current as a sensing for the charge. But if we look at the conductance graph through this quantum point contact region, so even though the current around this and this region is low, we can see the change in conductance and we can detect it. So it's not like it's not measurable here. So it's still measurable through this quantum point contact. And this is the reason why we are using quantum point contact as a sensor to for the charging and discharging event, not this current sensors. Okay. So in the next one, it is like the same thing, which is also like I have said before. So this is the sensing. I think there is a quantum dot region and there is a quantum point contact here. And we have, for this case, if you, these are the Coulomb blockade region, so no need to look at this. But the more interesting thing is here in this graph. Okay. So one thing for this graph, one the top graph, it is for the change in current through this quantum point contact region, and for the bottom graph, it is the current through this quantum dot region. So if you look at this graph, one thing you can notice is that for each Coulomb blockade oscillation, which you are seeing here in the below graph, you can see there is a corresponding change in conductance or the change in current in this quantum point contact region. Oh, this is one thing that you can easily notice. And the second thing that you should notice is that when we decrease or when we increase the gate voltage in negative direction, then the current is gradually decreasing, and this is the low current region. But in this low current region, uh, the conductance change in conductance, it is still measurable by this quantum point contact region. Okay, so this is like same conclusion, like why we are using quantum point contact instead of a current sensor. Next thing, it is like it's the same thing. So instead of we now we are using the quantum point contact uh, to sense the charging and discharging event in a double quantum dot case. So if you recall, for the double quantum dot case, if you look at the charge stability diagram that we have seen earlier, so charge stability diagram, because it's like a honeycomb pattern, because now we have a two gate voltage which controls the tunneling of electron through this double quantum dot region. So for double quantum dot, we see this honeycomb shaped pattern. But let us see whether we are seeing the same honeycomb pattern when we sense the charging and discharging event through this quantum point contact. Instead of the double quantum dot, we are sensing through this quantum point contact region. So if you look at this graph, this is like you can see that it is showing the variation of current through this quantum point contact, which is GLS, as a function of this gate voltage, the gate voltage applied to this double quantum dot. So you can see the same honeycomb pattern. So it's like no information is lost if you sense the charging and discharging event through this quantum point contact region. And the main advantage of using this quantum dot is that in addition to the information that we had earlier, we'll see more information about the tunneling event if you use a quantum point contact. So what I mean is that if you look at this graph, if you look at this plot, so this is the stability diagram that we have seen earlier. That is, what is the variation of current through this quantum dot as a function of this gate voltage. And if you recall, for this honeycomb shape pattern, the current is non-zero around this charge triple point. So that is why we are seeing non-zero current, non-zero value around this charge triple point, and the current in this region, they are zero because the current is the charge configuration are constant in this region. That is why you can see these are all black. Only this shows a colored region where we see the tunneling of charge carriers through this double quantum dot. But if you look at the charge stability diagram, if you through this quantum point contact, you can see that in addition to this charge triple point, we are seeing the variation, how this current is behaving around these lines, also around this charge degeneracy line. So that means if you use a quantum point contact, you can get additional information like the tunneling event happening in the double quantum dot, and what is the interdot tunneling. So it like more information you can get it from here. So that is why using quantum point contact is more advantageous than using the current sense. So till now, do you have any doubt in the concept? If you have any doubt while I'm covering the lecture content, feel free to write in the chat box. So I will try to make the concept more clear. Okay, just let me know so that I can stop at that moment and let me and clarify your doubts. Okay. So in for this part, bandwidth limit. So this quantum point contact or the single electron transistor, they have certain bandwidth limit. By bandwidth limit, we mean that we can't sense the charging and discharging event below certain time scale. So below some time limit, we can't sense. Even though the charging event is occurring, we can't sense it. So this is decided by the bandwidth limit. So this we'll see in our next slide. So for now, let me just skip it. Okay. In the next part, in the previous content, what we have seen, how we can use quantum point contact to measure the charging and discharging event. Now we'll see uh, what are the working principle of another type of charge sensor, which is the single electron transistor based charge sensor. Okay, so this single electron based transistors, what we mean by, if you recall the definition of the single electron transistor, so they are like another Coulomb blocker devices. So that means there will be a quantum dot which will be tunnel coupled. This will be tunnel coupled to the source and drain. And also it is capacitively coupled to a gate voltage. So this is the definition of single electron transistor. So that means we are using another Coulomb blocker device where we can see the Coulomb blocker oscillation to sense the charging and discharging event of nearby quantum dot. Okay. So this quantum dot, these are typically that we use for the sensing. These are typically large quantum dot. And this last quantum dot can show the Coulomb blockade oscillation. Also, this quantum dot, we can have different types of uh, SET for the charge sensing. It can be a normal SET or semiconducting or superconducting SET. So we'll see what are the difference between this normal SET and superconducting SET. For now, let us see what are the operating principle of this SET to measure the charge. So for this, as I said before, this is the circuit representation of a quantum dots SCT, which is used for sensing the charge. If you look at, as I said before, the quantum dot is relatively large and it is capacitively coupled to the gate. Also, it is tunnel coupled to the drain side, also to the source side. So these are typical values for capacitance of source and resistance of source, drain, and the gate. So for this SET, because they are Coulomb blocker devices, so that means if you look at figure, this figure, so when we change the gate voltage, so that means there will be a Coulomb blocker oscillation whenever the condition is satisfied for to get the Coulomb blockade oscillation. So that means we'll see a peak in the current right? This is the peak in the current. So that means if you for this devices, let's say intake rate, let's say we change the gate voltage by this delta Vj amount, then you can see that the current is changing by extremely. I think this is not visible. This is changing by a large amount. So even though we are applying a small gate voltage, then it's still possible to detect the current. So you can see there is a large change in the current. So that means we can use these characteristics of SCT to sense the charge. I think these graphs are already familiar to you. Mm, just to brief in details, so it's like this one is the current versus the drain voltage graph. So if you recall, we had earlier, you can recall this graph. We have seen this graph. Typically for ACT, the current is behaving like this. Up to the charging energy, the current is zero. But beyond this charging energy, we'll see the current will increase because of the Coulomb block oscillation. And this type of IV curve, we can change it if you change the gate voltage. So when we change the gate voltage, we can make the graph look like this, then it will now look like this. Then gradually we see a ohmic behavior when we apply sufficient gate voltage. And this we have, these are the effect of gate voltage on this IV characteristics. And for this SET, we also see the Coulomb blockade oscillation, where we see peak in the current, and this periodicity is in the order of E by Cg. So these are some of the concept that we have seen earlier. Now let us see what are the difference between a normal SET and a superconducting SET. Just give me a minute. Okay. So if you look at the, let me take out. So for normal SET, if you look at the graph, normal SET and we have superconducting SET. For normal SET, we have a IV characteristics which looks like this. We can see the effect of Coulomb blockade oscillation, and when we change the gate voltage, it can be changed, and we will see a ohmic behavior of IV characteristics. But when we look at the superconducting SCT, because if you recall, so in superconducting material, we have Cooper pairs, also we have a quasi-particles. So that means the IV characteristics now will have a two reason. One is for the Cooper pair and another one is for the case where the quasi-particle takes parts in the charge transport. So if you look at, so it's like for Cooper pair, you will see a variation like this. And for this quasi-particles, you will see a variation like this. This is the another. This is the main one of the difference between a normal SCT and a superconducting SCT. In superconducting SCT, because of this Cooper pair, we will see a sub-gap feature, and because of this superconducting gap, we'll see a reason. This charging and discharging event, or the we can say that the uh, Coulomb charging effect of these quasi particles, they are shifted by this superconducting gap. Here we don't have any signature of superconducting gap, but we'll see a signature of superconducting gap for this superconducting acid. And what is the next difference? This is the first one. Next one is the tunnel resistance. So to see the Coulomb blockade effect for this normal or semiconductor acid, we need that each tunnel resistance or resistance between the junction, it should have a value greater than equal to h by a squared, and this is value 25 point I think 83 for this normal and semiconducting acid. But for superconducting acid, because we have two types of charge carrier, we can see that we found that for Cooper pair, the resistance of this, the tunnel resistance, it should be greater than h by 4 is square. And this has a value of 6.45 kilo for the superconducting, for the Cooper pair, to see the Coulomb blockade oscillation for the Cooper pair. But for the quasi-particle, if you want to see the Coulomb blockade oscillation, the condition is normal, which is for the what we have for the metal and semiconducting case. That is RST, it should be greater than h by e square, which is 25.83 kilo. So these are the main two difference between a normal acid and a superconducting acid. And based on the condition, you can tell what are the whether there is a Coulomb blockade oscillation in the IV characteristics because of this charge, because of superconductor, because of this copper pair or the quasi particle. So if you look at the, if you just look at the what is the resistance of this total resistance of this device, then you can tell whether the copper pair is taking part in the transport, or whether there is a signature of copper pair or the quasi-particle Coulomb blockade oscillation in the IV characteristics or not. So this all depends on the tunnel resistance requirement. So you can see that for copper pair, the resistance requirement is quite low. It is in the order of 6.45 kilo ohm. But for a quasi-particle, we have the resistance which is quite higher, like it is 3 times of 6.45, so around 25.83. So that means if you are given a resistance, let's say you are given in the question, you are given a resistance, tunnel resistance of the device, then you can see, you can tell whether there is a Coulomb blockade oscillation of copper pair or the quasi particle. So this is what has been explained in this graph. So let's say you have a total resistance which is varying from 58 to 24 kilo. So that means this is the total resistance. And if you just assume that the resistance between the quantum dot and the drain, also the quantum dot and the source, they are equal. So that means the resistance of each tunnel junction, it is half of this total resistance. So in this figure, we are varying the tunnel resistance from 29 kilo ohm to 19 kilo ohm and 12 kilo ohm. So keep in mind that whatever condition that we are making for this tunnel resistance, it is for the uh, resistance of each junction, not the total one. So that is why we are dividing it by 2. So if you look at the first one, it is tunnel resistance, which is 29 kilo ohm. That means it is greater than 6.45, also greater than 25.83. So that means you can see both Coulomb blockade oscillation for Cooper pair, also the quasi-particle. CP for Cooper pair, QP for quasi-particle. And for 19 kilo ohm, you can see that it is much lower than 25.83. So that means there won't be any Coulomb blockade oscillation for quasi-particle, but we can see the Coulomb blockade oscillation for copper pi. And the same is the case for 12 kilo ohm because it is much less than 25.83. So that means you can see the Coulomb blockade oscillation for copper pair, not for the quasi-particle. Okay. So these are some of the examples of the SCT that has been used for sensing the charge. One is graphene SCT, another one is semiconductor SCT, and I think last one is double quantum dot SCT. So just let us just go through in brief what does it says. So as we have seen before, this SCT, these are large quantum dot SCT, and these are placed uh, to the region where the electron is tunneling through this dot, and we are sensing this electron tunneling by this SCT. Okay. If you look at the top graph, this is the conductance variation for the dot, like for this. This is for the conductance variation for the dot. And this variation is the conductance variation for this SCT. And the bottom one, it is the for the SCT, but now we are plotting what are the change in current versus the voltage instead of directly measuring the conductance. So if you look at the top graph, what is the variation of conductance in through this quantum dot, like this region, you can see the Coulomb blockade oscillation, and as we change the Coulomb, change the gate voltage, you can see it's not easy to measure the current in the low current region. Now, if you look at the SCT, whenever one thing you can see that you can see a graph like this. There is a slow oscillation of behavior like this. And this graph, it is due to, because you can see that SCT is also a Coulomb blocker device. Also, there is a Coulomb blocker device here. So that means if you change the gate voltage here, it will be also get affected. But because the dot is quite less, the effect is quite low. And because of this interdot effect, we see a slow oscillation like this. And another thing that we can notice that whenever there is a Coulomb blockade oscillation, we see a sharp change in the conductance in this graph. Okay. So to measure these peaks effectively, so you can see that these peaks are overlapped with this slow oscillation. So to remove this slow oscillation, what can be done is that we can take the derivative of the current through this SCT with respect to the gate voltage. So when we do that, then this slow oscillation can be removed. What we have is only the peaks in the current, change in current, and this is because of this charging and discharging event through this dot. Okay. So in this way, we can we can use the graphene SCT to sense the charge. And as I said before, uh, these are the charge stability diagram you can get for the graphene quantum dot. Okay. So even if you don't have ACT, you can see that the variation of current with respect to the gate voltage. It somewhat looks like this. But when we use SAT, we see the same features. So it's like no information is lost, and so we can use SAT to sense the charge. Okay. So in the next one, we have semiconductor SET, which shows the same behavior. So using this conductance graph and using the oscillation in this SET, we can use it as a sensor. There is not much to discuss here. For the double quantum dot based SCT, uh, what I can tell about is that so there is a quantum dot here, there is also a quantum dot here, and this is the superconducting single electron transistor SSSCT. So for this case, we have seen that if you recall, in the low current region, even if the current is low, we can still see oscillations in the current through this SCT. Okay, so that is why we are using SCT. Also, what the next one is, I think. Uh, Huh. And this slow oscillation, this is because of this interdot, the effect of dot on this superconducting acidity. I think this is fine for this double quantum dot. Okay. So let us see what has been covered in the last slides. That is how we can use the radio frequency ACT for ultra fast sensing. Till now, do you have any doubt in any of this part of the slide? For super, okay. So let us see what is radio frequency ACT and why do we need radio frequency ACT? Why don't we use the QPC and the ACT based sensor that we have seen earlier? So we have seen why we have started from, let's say, conventional FET based sensor. And we have discussed why we can't use this conventional FET-based sensor to sense the charge, which can have time scale in the order of millisecond. Then we have discussed the QPC and the SCT-based sensor, which can be used for to sense the charge, which is, I think, this also have time scale in the order of millisecond or below that. And now we'll see the radio frequency ACT. So just to tell you in brief why we use the RF is that we want to sense the charge which has time scale much lower than the millisecond, like which this if the charging and discharging event, if you want to sense the tunneling in the microsecond or the nanosecond region, then using QPC and SAT, it's not possible. But if you use RF SAT, then it's possible to sense this charging and discharging event, which is in the order of microsecond to nanoscale region. Okay, so and as we'll see, this QPC and SAT based sensor, they are limited by the bandwidth issues and the impedance mismatching, which can be overcome by this RF setting. So let us see in the details. So the charge motion, it can be through a device, or let's say we have a device and we are measuring the charge. Then the transport can be uncorrelated, or it can be correlated transport. This we have seen in our first lab session. What are the uncorrelated and what are the correlated transport? So if you look at the correlated transport, then it's possible to suppress the noise level. So we'll see sort noise suppression and bunching and anti-bunching effect in the correlated transport. So for this transport where the noise level is much lower. So if you look at the time scale of different type of event in different system, like it can be self-assembled quantum dot, or it can be a gallium arsenide two-dimensional electron gas. So for all these case, you can see that the time scale is in the order of microsecond or to extent of nanosecond or millisecond. So, but what we need that for ultra fast sensing, we need to design a sensor which can sense sense the charging and discharging even in much faster rate. So for this, so let us first discuss what are the bandwidth limit of the QPC based sensor or the SCT based sensor. This has been covered in this slide. So for QPC based, let me take a slide. Okay, so if for QPC based charge sensor, you can, as I have said before, we are measuring the current or the peak around this transition point, and we'll see peak in the change in conductance graph. But this type of design, they don't tell us about any temporal information about the quantum dot, like how long this quantum dot is inside this, how long the electron is inside the quantum dot, and how fast it tunneled outside this quantum dot, or what is the uh, electron occupation probability of this quantum dot. So this information is not uh, clear in this I versus V graph. And this can be to get this temporal information, what we need that the variation of current with respect to time. So this graph will show how long the electron is inside this quantum dot, how fast it is tunneling, and what are the uh, occupation probability of this quantum dot. So just to mention, I think we have one few more slides, then we'll start our questions that we want to solve. Okay. So if we look at this graph, this one, so we can see that there are graphs like this. So when we measure the current with respect to time, so we can use oscilloscope to record this variation. So for this case, what we can see that one is there are high level current and there are low level current. So this high level current means this is also mentioned in this graph. So high level current means the electron is tunneled out of this quantum dot, and the low level current, it means the electron is inside the quantum dot. So, and we are plotting this event as a function of time. So that means if you just look at these graphs, it can say how long, what is the time required for the electron to go from inside to the outside. Okay. And you can see that there are many random tunneling event that can give you other additional information. And this is also experimentally seen in a indium arsenide self-ascent quantum dot, where you can see the same type of behavior with respect to time. Okay, so for this case, you can see that this tunneling event, they are quite random. So bandwidth here, this bandwidth, they are they are this bandwidth, these are decided what is the bandwidth of circuit and what is the bandwidth of the external amplifier that we are using to measure the current. Okay, so what I mean is that I think this is one of the current versus time measurement which has been done in this sample. So you can see that here they have used IV converter to increase the bandwidth of this charge sensor. So you can see that you will see a tunneling event, and whenever the current is high, that means electron is tunnel out, and whenever the current is zero, the electron is inside this quantum dot region. And using this, we can achieve a detection limit which has order of 10 microsecond, not below the 10 microsecond. But what if we need charge detection in the order of nanosecond? So for that case, we need the radio frequency SCT. So as I have said before, the QPC, also the SCT, the bandwidth of this temporal information, they are decided by the circuit as well as the amplifier. So let us see what I mean by this. So if you generally look at what is the charging and discharging event inside this quantum point contact, then the intrinsic bandwidth, this is in the order of terahertz. But if you look at the temporal information, then a terahertz means 10 to the minus. In the time scale, it will be, okay, let me take, it will be in the order of 10 to the minus 12 second. But if you look at the temporal information, the orders like here, you can see that these are in the order of millisecond. So what is deciding this? What is making this bandwidth reduced from 10 to the minus 12 to 10 to the minus 3? Why we are not seeing this 10 to the minus 12 second? Why we are not able to detect the charging and discharging event in the order of 10 to the minus 12 or picosecond? So this is because of this. One is the impedance mismatch, one is the RC time constant, and one is the low frequency oscillation. So uh, by impedance mismatch, what we mean? So this is, let's say this is the device under test, and we have connected it to the external circuit to measure this IQPC and to get the graph of, let's say, the temporal graph like this. So this device under test, which has QPC, also the quantum dot region, they have relatively high impedance. And these connecting lines or this circuit that we are using to measure the current, there is certain capacitance, right? And because of this high impedance and the capacitance of this transmission line, so there will be impedance mismatch at this interface. And because of this impedance mismatch, what we'll see, this whatever signal we are getting from this device under test, this device, then it will get reflected here, also it get reflected here. So that means we are losing the information because of this impedance mismatch. And this impedance mismatch, they decrease the bandwidth. Also, the as we have seen before, the RC time constant, it is in the order of millisecond. So that is why we are not able to detect in the order of picosecond. And there is a low signal to noise ratio because of the 1 by f noise, low frequency operation. So because of this, we see that the signal is getting reduced because of the low frequency oscillation. So these are the limiting factor why the ultra fast sensing is not possible through the QPC or the SDPS device. So what we do to sense the charge in ultra fast time scale. So for this we use the radio frequency reflectometry or radio frequency SET. So in brief, what we do is that for this case, we integrate the SET to a um, high frequency LC tank circuit. So from this figure, you can see that we are integrating the SET to a high frequency LC tank circuit. And instead of measuring the current to sense the charge, what we do in the RF SET is that we measure the reflected power through this transmission line using this radio frequency SET. Okay, so that means when we integrate the SET through this high frequency LC circuits, now what we do next is that we uh, pass the high frequency uh, signals, the RF carrier signal. We pass this RF carrier signal through this high frequency TAN circuit. And because of that, this RF carrier signal, we pass it through a 50 ohm transmission line. So this frequency will now pass through this high transmission line, and it can interact with the SET. And depending on the impedance of this SET, also this transmission line, then we'll see reflected power and reflected peak. So what will happen during the charging and discharging event of the quantum dot, which is close to the SET, is that so when there is a charging or so this SET, they typically behave like a variable resistor. So whenever the charging and whenever the conductance or the current through this SET changes, then this resistance will also change. And what will happen now? So whenever there is a charging and a discharging event, that means the RSET will change. So let me take a slide. So whenever there is a charging and discharging event, the RSET will now change because of this Coulomb blockade oscillation. Coulomb blockade oscillation, they will change. And this RSET, because of this change in RSET, so what will happen? The impedance of tank circuit, it will also change. That means there will be impedance mismatch with the transmission line Z0, or I think it's written as Z0. So there will be impedance mismatch and there will be a reflection of the signal depending on the resistance of RSAT. And using that reflected signal, then we can sense the charging and discharging event. Okay. So this is in brief what are the operating principle of radio frequency SAT. Okay. I think this is let us start solving the questions now. Please go through the question once, then I will try to solve. The question is, which one of the following represents the electron occupancy for a superconductor in its normal and superconducting states. Okay, I think two graphs are missing here. So let me draw it. There is another graph, C. First one is like this. This first one is for, this is for normal state. This one is for superconducting state. Normal state, superconducting state. So there are four options, and you need to find out what are the, which of this following correctly shows the electron occupancy of normal and superconducting state as a function of energy. Recall that f of E is the probability that the electron will occupy for a given energy E, and the and we have depending on the normal state and superconducting state, they will show different type of electron occupancy. So just try to recall what is the behavior of normal state and what is the behavior of superconducting state. How the charge transport in normal state is different from the superconducting state. So once you find out that, then it's quite easy to see what are the which of this following graph correctly shows the electron occupancy as a function of energy. So I will give you, let's say, 1 minute, and I will solve the question after. Okay. So for this case, if you recall, what are the so if you recall the normal state, so normal state, the charge transport is happening through this electron charges. Okay, so that means electrons, if you recall, these are fermions and they have spin half integer, half of integral multiple of half spin. So that means for normal state, we have electrons and these have half integral spin and they follow the Fermi-Dirac statistics. So if you recall the Fermi-Dirac statistics, f of e, this is written as 1 by 1 plus e to power e minus ef by kbt. And this for temperature, for a non-zero temperature, you can plot f of e versus es like this. This is for the normal state. But if we look at the superconducting state, so if you recall in superconducting state, the charge transport started from Cooper pair. So Cooper pair, it is formed by the phonon exchange between electrons, where we have attractive forces, that is overcoming the Coulombic repulsion, and they are in a range, energy range of h cut omega d. So if two electrons, they exchange phonons and the attraction force is overcoming the repulsive Coulomb interaction, then it's possible to see the Cooper pair at low temperature. So that means for superconducting state, there are two electrons, and when they form the Cooper pair, they will linearly combine with each other and they have opposite spin and opposite moment. So that means the total spin of this Cooper pair, it is, you can say this is 0. So this is behaving like a boson. So that means it will follow Bose-Einstein statistics. So instead of Fermi-Dirac statistics that we have seen earlier, now we have a Bose-Einstein statistics because of the formation of Cooper pair. And the Bose-Einstein statistics, it looks like this. F of E versus E. So it's somewhat like this. For the boson for temperature T. So that means the answer to this will be option B. Okay. So let us see our next question. The critical magnetic field for a solid in superconducting state. Option A doesn't depend upon temperature. Option B, it increases if the temperature increases. Option C, it increases if the temperature decreases, or option C, none of the above. So the question asks about what is the dependence of critical magnetic field, SC, on temperature. So what do you think the correct option for this? Just recall what are the relation between the critical magnetic field and the temperature, which is the most common equation that we have seen in our earlier lecture. So if you recall, if you want to find out a critical magnetic field at any temperature, let's say T. So this is given by critical magnetic field at 0 Kelvin 1 minus T by Tc whole square. And if you want to plot it, so this is Sc versus temperature T, then we see a variation like this. So that means when we increase the temperature, so this is Tc, when we increase the temperature, then the critical magnetic field decreases. So it goes from a maximum value to a minimum value. So the correct option is option C. The critical magnetic field increase if the temperature decreases. Question number 12. I think it's better in this orientation. Okay, so there is a material which behaves like a superconductor below a critical temperature, Tc, and is a normal conductor above Tc. A magnetic field B equal to Bz cap is applied when T is greater than Tc. The material is then cooled below T equal to Tc in the presence of this magnetic field. Then which of this following figure correctly represent the correct configuration of magnetic field lines? So you have a so you have a superconductor which has a critical temperature Tc. Now you heated the superconductor. Now we are cooling it down by using this magnetic in the presence of this magnetic field. Then how the magnetic field lines will behave is a function of temperature. Like what will happen to the magnetic field lines for T greater than Tc or T less than Tc. So this is, I think you can easily find out the answer to it. For T greater than Tc, you can see that the superconducting state will vanish. So that means the magnetic field lines will pass through this material for T greater than Tc. So that means option A is the correct option, one of the correct option. Let us see option B. Option B says for T less than Tc, still the field lines can pass through the superconductor, which is not true because superconductor, they repel the magnetic field lines when they are in superconducting states. And for C, it shows the magnetic field lines, it's not able to pass through this superconductor for T less than Tc, which is true, right? It is in the superconducting state, so they will repel the magnetic field lines. Option D is also not the case. It shows for T less than Tc, you are seeing a magnetic field lines like this, so which is not possible. So that means the correct option to this is option A and option C. Question number 13, it's a numerical question. So there is a superconductor which has a critical temperature of 4.7 Kelvin at zero magnetic field and a critical magnetic field of 0.3 Tesla at 0 Kelvin. What is the critical magnetic field in Tesla at 2 Kelvin? Round off to 3 decimal places. So you need to calculate critical magnetic field at a given temperature 2 Kelvin in the unit Tesla. Okay. So I will give you some time, let's say 2 minutes. Just try to solve it, then I will go through the steps. So remember to look for the units. It's like if units are not correct, then uh, you may take wrong relation, then you may get wrong answer. Okay. For this case, I think even though you can take B or H, it doesn't matter. But for some cases, if you want to use that for calculating some other parameter, then it's quite important to look for the units. Okay. Solve it first, then I will go through the questions. So let me just tell what has been given to you. So there is a superconductor and it's given for zero magnetic field. So Tc is given 4.7 Kelvin and also for uh, critical magnetic field for temperature T equal to 0 K, it's given 0.3 Tesla. So you want to find out what is the critical magnetic field for T equal to 2 Kelvin. Okay, so let me just solve it. So if you recall, there is a relation that you can use to calculate the critical magnetic field for a given temperature 2 Kelvin. So this is critical magnetic field at temperature 2 Kelvin is critical magnetic field at 0 Kelvin 1 minus T by Tc whole square. And the critical magnetic field for 0 Kelvin, it's given, it is 0.3 Tesla. And 1 minus T is 2 Kelvin. Tc is given 4.7 square. So this will give critical magnetic field. I think 0.246 Tesla. So answer is 0.246. Okay. Question number 14. It's a conceptual question. In the AC Josephson effect, a supercurrent flows across two superconductors separated by a thin insulating layer. And this is kept at a electric potential difference of delta V. What is the angular frequency of resultant supercurrent which is given by? What is the angular frequency of supercurrent which pass through this AC Josephson? This is direct formula based answer. So you can easily guess that omega is 2e delta B by h cot. Okay. Question number 15. A DC voltage of 2 microvolt. It is applied across a AC Josephson junction. The frequency of the emitted radiation could be. So DC voltage is given. This is 2 microvolt. You want to find out what is the frequency of emitted radiation through this AC Josephson effect. Let me give you 2 minutes, then I will show you the steps. This is question number 15. It is related to question number 14. So if you know the angular frequency, then you can find out what is the frequency. How many questions we have? Okay, this is the last one. Then we'll start the problems related to week 10. So as we have seen in question number 14, so if you want to calculate what is the angular frequency or the frequency related to emitted radiation for AC Josephson effect, so we have omega, it is 2e delta V by h cot. Omega is nothing but 2 phi f, 2e delta V by h cot. So this is f is 2e delta V by h. So that means we can, so delta V is given and E and H, this we are known. So 2 1.6 10 to the minus 19, 2 microvolt, and H is 6.63 to 10 to the minus 34. So this will give a value of 967.2 megahertz. So the frequency of this emitted radiation for this applied voltage, it will be option B. Okay, let us say question number 16. It's a conceptual one. What is the physical origin of AC Josephson current when a DC voltage is applied across a Josephson junction? Option A, time-dependent phase difference leading to an oscillating supercurrent. Option B, thermal activation of quasi-particle over the superconducting leads. Option C, generation of normal current due to ohmic resistance in the barrier. Option D, charge imbalance between electrons and holes in the superconducting leads. This is quite easy to guess. The reason why we are getting a DC voltage across the Josephson junction because of this AC Josephson current. So this is because of the time-dependent phase difference, which leads to an oscillating supercurrent. Okay. So this is all about the problems related to week 9. So let us start solving the problems related to week 10, which is based on the QPC or the affinity-based charge sensor. So question number A, question number 1, in a QPC-based charge sensor, the conductance through this QPC changes rapidly whenever there is a Coulomb blockade oscillation in the nearby quantum dot system. So whether this statement is true or false, you need to find out. So in a QPC-based charge sensor, the conductance through this QPC changes rapidly whenever there is a Coulomb blockade oscillation in the nearby quantum dot system. You can easily guess, so this is true. So if you look at the graph of I dot versus GQPC, so we have seen that whenever there is a Coulomb blockade oscillation, we see there is a peak in the conductance. Okay, so this statement is true. Question number 2, you need to identify which is the incorrect statement from this given option. So option A, current measurement can be used for charge sensing when the electron transmission rate is of the order of 10 to the 3 Hz, or you can say kilohertz. Option B, current measurement can be used in the high electron transmission rate, which has a rate greater than megahertz regime for charge sensing purpose. Option C, the thicker source and drain barrier at high gate voltage lowers the tunnel rate through a device. Option D, measuring the current in the few electron regime is not a good choice for the charge sensing due to the low tunnel current. Which of this you think is the incorrect statement about this charge sensor? So if you look at option A, the current measurement can be used for sensing the charge where electron transmitter rate is of the order of kilohertz. So this is not true. And this is this you can see from this graph. This we have discussed in the first part of our live session. So if you look at this figure, IV characteristics, you can see that for 10 to the power 3 hertz or kilohertz, the current is below the noise floor. So that means we can't measure the current. We can't measure the current because it is below the threshold limit of the device. So that means for this reason, it's not possible to see the current measurement. So option A is a correct option, incorrect statement. Let us see option B. Current measurement can be used in the high electron transmitter rate, which has rate 10 to the 6 Hz or megahertz regime for charge sensing purpose. So this is true, and this is also quite obvious from the same graph. So if you look at 10 to the 3 years here, so beyond 10 to the 3 years, the current is above the noise floor. So that means it's possible to sense the single charge event. So that means you can use it for charge sensing purpose. So option B is correct. Option C, thicker source and drain barrier at high gate voltage lowers the tunnel rate through a device, which is true. This we have seen by varying the gate voltage. And option D, measuring the current in the few electron regime is not a good choice for charge sensing due to the low tunnel current, which is also true, right? So that means the incorrect statement in this question is option A. Okay. Question number 3. Which of these following is true for classical FET based charge sensor? Option A. This classical FET follows the classical transport, which can lead to classical noise. Option B. They have large geometry and capacitance of the device, which limits the charge sensitivity. Option C, it can be used for ultra-fast charge sensing, which has time scale in the order of microsecond to nanosecond. Option D, they are able to detect one electron in 100 milliseconds. Which of these following statements are true for the classical field effect based charge sensor? So this part also we have covered here. So if you look at this classical charge sensor, we are able to detect one electron in 100 milliseconds. And they have large geometry, they have large capacitance. So that is why the charge sensitivity get lowered and there will be a classical noise because of this classical transport. So that means this option is correct. This is also correct. And we can detect one electron in 100 milliseconds. But if we look at option C, it says that it can be used for ultra fast charge sensing, which has order of microsecond to nanosecond. So this is not true. So that means the answer to this question is A, B, and D. Question number 4. Which of these following which of these following are applicable for a correlated transport of charge carrier? Option A, Bunching and anti-bunching effect. Option B, it can show short noise suppression. Option C, both A and B are correct for the correlated transport. Option D, none of the above. This is also quite straightforward. The correlated transport can show short noise suppression as well as bunching and anti-bunching. So that means option C is the correct option. Okay, both short noise suppression and bunching and anti-bunching effect we can see in the correlated transport. Okay. Question number 5. There is a plot given to the right side of this question. So the curve shows a plot of conductance of quantum point contact, which is used for charge sensing of the nearby quantum dot. Point A and B indicate the different region on this conductance graph, with A refers to the flat plateau region. It's a point on the flat plateau region, and B refers to the point between two plateaus. Which of this given point can be used to get a better charge sensitivity for this quantum point contact based charge sensor? So can you use A for the charge sensing or can you use B for the charge sensing? Which of this region is best for sensing the charge in a QPC based sensor? So I will give you 2 minutes to think about it and I will show you the answer. Okay, so let us see the answer to it. So option A is point A, option B is point B, option C is both point A and B, option D cannot be decided. So the answer to this is option B. So if you look at this conductance versus the voltage curve, GQPC versus the gate voltage. So we see the plateaus and we see steps. And the point A is the flat plateau region, point B is around the point where the conductance is changing. So that means if you plot the variation of conductance as a function of the gate voltage, you will see in the flat region there is no variation of conductance, right? So that means the DI QPC or sorry DZ QPC over DV gate, this will be a flat for point A. But if you look at around point B, then you can see that the conductance is changing rapidly. So that means if you plot this variation of conductance, we'll see a peak around point B. So that means you around this point, you can use it for sensing the charge. Okay. So answer is option B. Question number 6, it's a conceptual question. In a QPC based charge sensor, which of these following limits the bandwidth of charge sensitivity? Option A, impedance mismatch. Option B, RC time constant of measurement circuit. Option C, 1 by F noise in the low frequency operation. Option D, none of the above. For QPC based charge sensor, what is deciding the bandwidth? You can easily tell all these three options are correct. They can lead to the lowering of bandwidth in a QPC based sensor. So option A, B, and C. Okay, question number 7. The tunnel resistance requirement to observe the Coulomb blockade oscillation for Cooper pair transport in a superconductor SCT is. So, what is the tunnel resistance requirement for superconducting in a superconducting SCT for Cooper pair? Option A H by 2 E square, option B H by 4 E square, option C H by E square, or option D 2H by E square. Which of this is the correct option and which of this is the minimum tunnel resistance requirement that is required to see the Coulomb blockade oscillation in a Cooper pair inside a superconducting SCT? So if you recall, while discussing the difference between a normal SCT and a superconducting SCT, we see that a normal SCT, the tunnel resistance requirement is that RST, it should be greater than 25.83, which is H by 2 square. Sorry. And I think I'm correct. Let me see. So the factor 2 is not there. So that's what I was thinking. H by E square, not H by 2 E square. But for a Cooper pair, uh, so this is valid for normal SCT and the quasi-particle transport in a superconducting SCT. But for Cooper pair, RST, it should be greater than H by 4 square. So for Cooper pair, we'll get a tunnel resistance requirement, which is H by 4 square. So option B is the correct option. Question number 8. When no measurable current is flowing through this quantum dot, the QPC still detects single electron charging event. This is possible because the QPC option A directly measures the dot current, I dot. Option B requires the dot to be in Coulomb blockade region with zero tunnel rate. Option C, it senses the change in conductance when electron tunnel through the quantum dot. Option D, none of them. So the question asks, even though there is no measurable current through this, let's say we have a dot region here, and we have a QPC around this region. So even though there is no current through this dot region, why we see a single electron charging event through this QPC? Option A directly measures the dot current, which is not true. Quantum point contact doesn't directly measure the dot current. Option B, it requires the dot to be in super Coulomb blockade region with zero tunnel rate, which is not true. If the zero tunnel rate is zero, that means we won't see the peak in conductance graph, so we can't measure we can't sense the charging and discharging. Option C, since it senses the change in conductance when electron tunnel through this quantum dot, which is true. So this is the reason why we are seeing we are able to sense the charging and discharging event, even if the current through this dot is zero. So the correct option is option C. Question number 9. The impedance of radio frequency SCT of resonance depends on inductance of tank circuit, resistance of the device, option C, capacitance of the device, or option D, none of the above. I will give you 1 minute just to think about what is the answer for this. So if you recall the relation, so Z, which is the impedance of radio frequency city at resonance. So this is given by L by R CD. So that means it depends on inductance as well as resistance as well as capacitance. So answer to this is A, B, and C. All these three are correct options. So let us see question number 10. For a for a superconducting ACT of total tunnel resistance 38 kilo ohm, which of these following characteristics are not observed in the IV graph? Option A, Coulomb blockade oscillation due to the Cooper pair. Option B, Coulomb blockade oscillation due to quasi-particle. Option C, both A and B. Option D, none of the above. So you have a superconducting ACT and it's given the total tunnel resistance is 38 kilo. Then which of this following you can see in the you can't see in the IV characteristics, whether you can't see the Coulomb blockade oscillation because of this Cooper pair or because of the quasi-particle, or you can't see both the Coulomb blockade oscillation because of Cooper pair as well as the quasi-particle, or the answer is none of them. So if you recall, so if you assume that the tunnel resistance for the source to dot and from the dot to drain, they have the same, they are nearly symmetric. So that means you can take the tunnel resistance of each junction is half of this total tunnel resistance. So this will be 19 kilo. And if we recall for Cooper pair, RST, it should be greater than H by 4 E square, which is 6.45 kilo ohm. And for quasi-particle, this RST, this should be greater than H by E square, which is in the order of 25.83 kilo ohm. So this tunnel resistance requirement is to see the Coulomb blockade oscillation. To see the Coulomb blockade oscillation, you need to have a minimum tunnel resistance of 6.45 for the Cooper pair. Also, for the quasi-particle, you need a minimum tunnel resistance of 25.83. And you are seeing that for this given superconducting ACT, the tunnel resistance is 19 kilo ohm. So that means if you look at the Cooper pair, the minimum is 6.45, which is less than the 19 kilo ohm. So that means you can see the Coulomb blockade oscillation because of the Cooper pair. This is possible. But if you look at the quasi-particle, it requires a minimum tunnel resistance of 25.83, which is much lower than this 19 kilo. So that means you can't see the Coulomb blockade oscillation because of this quasi-particle. So only in the IV characteristics, you will see only the Coulomb blockade oscillation because of this Cooper pair. So answer to this is option A. Question number 11. A designer wants to maximize ACT charge sensitivity by adjusting the island size. What is the main reason that shrinking the island and thus the reducing the total capacitance improves the sensitivity? Okay, so it's telling that what is the reason behind increasing the improvement of sensitivity when we shrink the island or when we decrease the total capacitance. Option A, it decreases the island capacitance, allowing higher bias currents. Option B, it increases the charging energy EC, making single electron charging steps energetically more distinct. Option C, it ensured that tunneling becomes completely elastic and independent of energy. Or option D, it reduces the gate capacitance to nearly zero. So the gate no longer affects the island. So if you look at this, the correct option is I think option B. It increases the charging energy, which makes the single electron charging event steps energetically more distinct. So this reason is that you can look AC is E square by tau C sigma. So when we shrink the size, so when we decrease the device dimension, so that means we are decreasing the total capacitance. So this will increase the charging energy. So increase in the charging energy means we will see a sharp Coulomb blockade oscillation. So the Coulomb blockade oscillation will be sharp for the design where the charging energy is much larger. Okay. And the separation between them is also quite large. So that means these peaks don't overlap. So we can still single out the charging and discharging event. Okay. So this is the reason why you can uh, shrink the size and you can improve the sensitivity. So we'll stop for today. Uh, we have covered all the concept related to this week. So in the next week, we'll try to cover week 11. So thank you for joining the session. So we'll meet on next Friday, same time from 6 to 8. Okay, so to see what is the concept of week 11 and try to solve your problems related to it. So for now, goodbye everyone.